The moving magnet and conductor problem is a classic thought experiment in physics that brilliantly demonstrates the interconnectedness of electricity and magnetism and the crucial role of reference frames. It was a conceptual puzzle that perplexed 19th century physicists and served as a foundational problem that Einstein addressed in his 1905 paper on special relativity. The experiment consists of two scenarios, both of which produce the same physical result but are explained differently depending on the chosen frame of reference. In the first scenario, a bar magnet is moved toward a stationary closed-loop wire. An observer in the lab frame explains the induced current using Faraday's law of induction. As the magnet approaches, the magnetic flux, phi_b, passing through the wire loop changes. According to Faraday's law, this changing flux induces an electromotive force, EMF, which in turn drives a current in the wire. The induced current is understood to be the result of a changing magnetic field creating a non-conservative electric field that exerts a force on the charges within the stationary conductor. In the second scenario, the magnet is held stationary while the wire loop is moved toward it. An observer in the lab frame still sees a current induced in the wire, but the explanation shifts. Since the magnetic field is static, there is no changing magnetic flux through the loop. Instead, the explanation relies on the Lorentz force. The free charges within the wire are moving along with the conductor through the stationary magnetic field of the magnet. According to the Lorentz force law, a charge moving through a magnetic field experiences a force, vec F equals Q, vec V times vec B, that pushes it along the length of the wire, creating the observed current. The apparent paradox lies in the fact that the same physical phenomenon, a current in the wire, is explained by two seemingly different mechanisms, an induced electric field in one case, and a magnetic force on moving charges in the other. This lack of symmetry was the central issue that Einstein's theory of special relativity resolved. He showed that the distinction between an electric and magnetic field is not absolute, but depends entirely on the observer's inertial frame. What one observer perceives as a purely magnetic force on a moving charge, another observer in a different frame may interpret as an electric field acting on a stationary charge. This thought experiment is a powerful illustration that the laws of physics must be consistent across all inertial reference frames. The moving magnet and conductor problem is more than a historical curiosity. It is a profound lesson in the relativistic nature of electromagnetic fields, demonstrating how the concepts of electricity and magnetism are inextricably linked and ultimately different manifestations of a single, unified electromagnetic force.